Hello world, it's Siraj, and AlphaGo Zero is DeepMind's popular AI that beat the world champion at the game of Go in a match that was watched around the world. In this video, I'll explain how it works using code and animations. If you're new here, don't forget to hit the subscribe button to stay up to date on my latest AI content. DeepMind shocked the world in 2016 when the initial version of AlphaGo beat 17-time world champion Lee Sedol. Just a year later, AlphaGo Zero, an improved version that, unlike its predecessor, was trained without any data from real human games. It learned only by playing against itself, beat the world champion. In regard to AlphaGo, Ian Goodfellow, a researcher at Google Brain, noted that we're starting to see AI move beyond what humans can tell the computer to do. And the AI can actually figure out how to do something better than the best human. The idea that AI can think in ways we can't was exemplified when AlphaGo played move 37 against Lee Sedol. It was a seemingly bad move to the human master, but it turned out to be crucial to its success. It had learned a way of playing that surpassed the 2,000 years worth of strategies humans had come up with. But that should not seem scary. The dot product operations became self-aware? If we can combine this alien way of thinking with our own to solve problems, there's nothing we can't do. The possibilities really are endless, whether it involves discovery or creativity. We just need to make sure everybody understands how this power works. A traditional game of Go starts off with an empty board, and let's be real, probably some tea. Both players have an unlimited supply of pieces called stones. One taking the black stones and the other takes the white stones. The goal of the game is to use your stones to form territories by surrounding vacant areas of the board. It's also possible to capture your opponent's stones by completely surrounding them. Both players take turns, placing one of their stones on an empty point at each turn, with black starting off. These stones are placed on the intersections of the lines, and once played, stones cannot be moved, but they can be captured. When the game ends, both players count 1 point for each vacant point inside of their own territory, and 1 point for each stone they've captured. The player with the larger total territory plus captured stones is declared the winner. With so many possible positions to play here, there are endless tactics to learn to try and master this millennia-old game. So when thinking about developing an algorithm for Go, we need to start listing the properties of this game in a fundamental mathematical way. We know that Go is a discrete, deterministic game with perfect information, meaning there are individually separate and distinct moves and positions. Every move has a set outcome. There are two players competing against one another, and both players are able to see everything, the whole position of the board. It turns out that tic-tac-toe is another game that has those same properties. Life isn't though, unless you're Neo. If you were to develop an AI to beat tic-tac-toe, then we could write a script that would pick a move that results in the lowest score for the opponent. We know that there are 3 possible values for a given game state. Either it's a loss, a win, or a draw. So our script would try out every possible game state in real time, forming a tree of states. Then perform a depth-first search to find the optimal move to play. When we run our script, we'll find that it will always either win or draw with any human it plays against. But could we apply the same tree search to Go? Well, it turns out that there are more possible Go positions than there are atoms in the universe. So since Go is such a complex game with so many possible moves to play, using a brute force search to find the best one simply isn't possible using current computing hardware. We need a strategy to initially explore several possible moves on the board. then focus this exploration over time, as certain moves are found to be more likely to lead to wins than others. When our depth-first search method estimated the value of a given state in the search, both players must play optimally, choosing the move that gives them the best value, and this required computationally expensive recursion. But instead of making the players choose optimal moves, what if we computed the value of a state by making the players choose random moves from there on and seeing who wins? This is the basic idea behind the Monte Carlo tree search, the go-to algorithm for writing bots to play discrete, deterministic games with perfect information. It uses random exploration to estimate the value of a game state. A single random game can be called a layout, and if we play 1,000 layouts from a given position, X, and player A wins more than half the time, it's likely that the position X is better for player A than for player B. We can create a Monte Carlo value function that estimates the value of a state using a given number of random playouts. The code will be similar to the depth-first search code, but the difference is that instead of iterating through all move possibilities and picking the best one, we randomly choose moves. But random doesn't sound too intelligent, does it? What if we could have our algorithm choose a move using some knowledge of what moves are worth playing? But not by trying them all out, which would be very expensive computationally, but instead by computing a heuristic approximation of the true value of each move and choosing moves within playouts based on this heuristic. The UCT, or Upper Confidence Tree Score, can help with this. It's made for balancing both game exploration and exploitation in a sensible way by computing a heuristic value of a move V. V is computed using the aggregated score after playing a move in all simulations thus far, the number of plays of that move, the number of game states, and an adjustable constant representing the amount of exploration to allow. This equation helps balance exploitation by playing known moves with high values and exploration, trying out moves that have a low visit count, and updating the algorithm with this newfound knowledge of how valuable they are. Notice that UCT involves learning over time, whereas both DFS and plain MCTS were static. At first, UCT is exploring lots of game states, but as it collects more data, the random playouts become less random and more heavy, meaning it explores move paths that have already proven to be good choices, ignoring the rest. This creates a self-reinforcing cycle, becoming more skewed towards good moves than bad moves. But check this out. Sometimes two game states can have pieces in different positions, but the essential components of the situation are the same, meaning strategically, the difference in piece locations might not matter. To the UCT score, these are two distinct game states. But to humans, we could intuitively note that similar strategies would apply to both. It's essentially the same game state. Rather than having our AI memorize a heuristic value for every game state it finds and storing it in a hash table, what if it could learn heuristic values from images of the game board? AlphaGo Zero sprinkled in a convolutional neural network to do just that. It used a massive 20-layer residual network for this. This is a convolutional network that avoids the vanishing gradient problem common in neural networks, which makes them unable to learn long-term sequences, by creating a shortcut at each layer, which allows the gradient to skip over intermediate layers and reach the bottom during backpropagation without being diminished. While neural nets usually output a single fixed output, their network had two heads. One took the output of the first 20 layers and produced probabilities of the Go agent making certain moves, and the other took the output of the first 20 layers and outputted a probability of the current player winning. So, the training process of AlphaGo Zero for playing against itself in games of digital Go started off with initializing the residual network. It used 1600 Monte Carlo tree search simulations per move that it played and sampled about 2,000 positions from the most recent 500,000 games, along with whether that game was won or lost. For every move, it recorded the results of the MCTS evaluation of those positions, meaning how good the different moves in these positions were based on looking ahead and whether the current player won or lost the game. The neural network was trained using both the move evaluations produced by the MCTS search and whether the current player won or lost. At every 1,000 iterations of this process, the algorithm evaluated the current residual network against the previous best version. If it won the majority of the games, it would begin using it to generate self-play games instead of the previous version. And that's really it. It just used simulations to generate training data for its neural nets, then learned from them in a supervised way. In total, it took Google 40 days to train AlphaGo Zero to become the best Go player in the world, using 64 GPUs and 19 CPUs, which costs millions of dollars. While the hardware is expensive right now, those costs are dropping, and the idea of AlphaGo, an AI that's able to master such a complex game better than any human can by playing against itself with no human knowledge input, is dope AF. Hey, you made it to the end, you beautiful wizard you. Hit subscribe and connect with me on Twitter, Instagram, and Facebook for more developer education. For now, I've got to search a tree, so thanks for watching.